Hello everyone. In this tutorial, I'm going to show you how to make this tessellation shader. Um, the first steps will be going over how to make an unlit version just using shader code, and the second version will be getting it to work with shader graph. Just as a note, the shader graph part will only work if you're using Unity 6 or above, due to a feature they added in custom functions in shader graph called use pragmas. Um, so First thing we're going to do is create this basic tessellation shader, which you can just control by a distance and like a multiplier. But you might be wondering, what is tessellation? So, tessellation is basically when you have a lower poly mesh and you want to add a lot more vertices like in these images. What the shader does is it passes this data to the GPU and it creates it there. So you don't have to have a high poly mesh in Unity, or rather like imported. It will do all that work on the GPU for you. So that means less storage, less memory. It just does it all at runtime. And how we're going to be doing that is we're going to be creating a whole program and a domain program. So basically, in your normal shader, you've got your vertex program, which all the vertices on the triangles on your mesh are passed to this. It calculates some data and then basically just skips straight to the end and does the fragment program. So the fragment program is in your screen. It runs for every single pixel on your screen that the mesh is available in. And then it calculates the color and like the lighting data for that. And what we're going to do is we're going to take this whole program, and that's going to tell the GPU to basically split up the triangles into more triangles. And then in this domain program, we're going to sort of create the data for these new triangles, because the GPU doesn't really know that we need in them to actually have data, because they're just going to be at like the center of the object. They're not going to know where to go. So we're going to do that here. And this is also where you can do things like vertex displacement, which is usually why you want to have tessellation. Because other than that, it's generally kind of expensive to do. So if you don't need to do tessellation, it's advised to not do that. So we're just going to get started. I'm going to remove these planes for now. And we're just going to create an unlit shader here. So go to create shader and then URP unlit shader. And we're just going to call this tessellation. And go ahead and open that. Okay, so now that you've got that open, what we're going to do is we're actually going to create the whole method. So it doesn't really matter where you put it. I'm just going to put it above the vertex here. So what we want it to return is, actually, I'll go over what this does first. So the attributes are the data that is passed into the vertex function, and that's basically everything on the vertices. So if you go into Unity, if you make a plane, every single one of these points, you can go into shaded wireframe, by the way, that's how I'm seeing these. Every one of these points will have a position and stuff like UV data in the normal. And the center of these, like each triangle, doesn't really know that data, which is the point of the vertex function. The vertex function interpolates the data between the whole triangle. So if you were in the center of the triangle, it's going to have the average of the data of all of the vertices. So in here, in the vertex function, that's what it's doing. It's just transforming the vertex data into the varyings data, which is the pixel data. So up here, we're just going to return the attributes here, which is the vertex data. And we're just going to call this whole. And it's also going to take in an input patch of 3 attributes. Let's call it patch. So this is basically, it's sending a whole triangle at once, which is the input patch, and then you get 3 data points for each vertex in the triangle. And we also get the ID for each triangle that we're currently working on, which has this tag here. You can think of it as sort of in C# you have like attributes that you can put on like functions or fields, like serialized field is one you've probably used before. That's sort of like this. It's telling the GPU that we want this ID to have a certain function. Otherwise, it would just be like, well, why do you want this ID? It's just a number. I don't know what to pass in here. So for now, we're just going to return the data from the patch ID that we're currently working on. So it's just sending through the whole, all the triangle data, and then it's like, okay, you get this attribute right now. Now, if you go back into Unity, nothing's really happened because what we need to do is go up here and tell the GPU and the shader that we actually want this whole method to be run, pretty much. So what we're going to do is pragma whole, because this is the name of our whole method. The first whole is just telling you it wants it to run the whole shader. So now, if you go back into Theme, you can see a bunch of these errors here, and that's because we have to add some attributes, not this type of attribute, but like headers almost, to the whole method. So the first one it's complaining about is the domain. So what we want to do is go domain, and there's a few things here. You can use try, quad, or isolene. Right now our mesh is using triangles, as you can see, so we're just going to put in try. And now it wants the patch constant function. Basically what that is it's telling our shader how much we want to tessellate. So this can be kind of wherever, but it needs some new data. So we're going to create a new struct right here. So struct tessellation factors. And this is going to have some new data. So each triangle is going to have, it's going to be split along the edges, and this is basically going to tell it how we want it to be split, or how much we want it to be split, rather. So we're going to have the three edges of the triangle. They're all going to have their own data point, and this is sv underscore test factor. And don't forget your semicolons. And then there's also going to be a factor for the inside, which is just the center of the triangle, which is the inside factor. So now we're going to make the patch constant function. So what that is going to do is going to return the tessellation factors, and I'm just going to call this patch constant function. And this is going to take in the input patch of the attributes. And for now, we're just going to so we're going to create the tessellation factors, because unlike in C#, you cannot just create like new tessellation factors. That's not really how it works. Whenever you define a like a struct like this, when you create a name, then the GPU will create like memory for it. It will initialize this without having to add the new, but you need to add all the parameters yourself. So we need to create all the edge variables, and for now I'm just going to set this to 1 for all of them. And then we're going to return the tessellation factors. So now we go up here to add in the patch constant function, and you need to pass in the name of your function here. Make sure that's the same, otherwise it doesn't work. And now, oh sorry, this does not need to be capitalized. And it's also not function, it's just func. There you go. So it also needs partitioning. So basically, that's telling the GPU how exactly do you want the tessellation factors to be split up. So do you want it to be integer, so like only integer numbers, so like 1, 2, 3, or fractions. So we'll just do integer for now, and that is partitioning. And we also need the output topology. And so we add that here. You can see there, what we want now is we're doing triangles, and the underscore CW and underscore CCW are for clockwise and counterclockwise. So basically the way most 3D programs handle the like normals is that if the points are defined like 0, 1, 2 in a clockwise order, then they're pointing up. Or if they're defined counterclockwise, like 0, 1, 2, then they'd be pointing down. So that's why you can see on the bottom, you can't see anything, and on the top, you can see up. That order is not necessarily specific or like universal. Some programs do it one way, some programs do it the other way. So it really depends. But Unity does clockwise, so we're going to do triangle clockwise. And we also need the output control points. So basically, what that's saying is we're going to be outputting 3 data points for each hole because that's how many we're taking in. You can see we're getting an error here. That's because on the test factor up here, that should be inside test factor, not just inside factor. So now you can see we've got our plane, and nothing's really changed. But that's good because the shader has compiled. You can see, click on it, no errors. So now we move on to the next step where we create the domain method. So as I said earlier, that's the part that's actually going to interpolate the values and actually kind of create the new vertices. So this is going to return varyings because now we're in the fragment shader land. So it's created the vertex data, and now it needs us to interpolate it for the pixels. So we're going to take in the tessellation factors as well as an output patch of the attributes, and also some things called barycentric coordinates, which have their own tag as well. And just open that. And so you might be a little confused about these barycentric coordinates. So what they are is basically the GPU has created where it thinks the new vertice should be, but it doesn't actually have any of the info on it. So it creates these coordinates which are relative to the existing vertices on the triangle. I'm going to put up a little visualization here, but it's kind of based on if you have a point inside a triangle and drew a line to each vertice, then you would be able to get the coordinates based on the relative area of those triangles. Okay, so with these barycentric coordinates, we can now interpolate the data for each position we need. So basically, for everything inside these attributes, we need to interpolate them. So what I'm going to do is I'm going to create what's called a macro. I'm just going to call it interpolate. And it's going to take in the field name that we want to interpolate. And the way these macros work is they're not exactly like functions in that you can reference data that is in the function that you called it from. So if I go data.fieldName, so it doesn't know what data is, it's assuming where you call it from has something named data. And it's going to be also taking in this patch data. So index 0 of this patch, which is going to be one of the vertices, dot field name, which is the thing we're passing in here, is going to be multiplied by the barycentric coordinates, dot x, and then we're basically going to do that for every single point, and for y, and for z. And you can split up these functions using backslashes, so they don't all have to be on one line. And then semicolon at the end. So what we need to do now is create this data, which is going to be the attributes that we are interpolating into. So now we can call interpolate, and what we want to interpolate is position object space. That's what the OS stands for. And you can see it works fine, no errors. And we also need to interpolate the UV data, which is here. But now you can see it's returning, the domain method is returning varyings, but we have the attributes right now. So what we actually want to do is we're going to call the vertex method. So we're going to return vert and just pass in our data. And that's going to interpolate and create all the data for the varyings for us with just interpolating this vertex data. So now there's a small error now. You might not see it when you go back into Unity, but the vertex method is going to be called multiple times, which we don't actually want to happen. It won't really mess up anything, but there's not really any point. So we're going to create a dummy vertex method, and this is going to pretty much just return what exactly is put in. So now we can go up here, replace the vertex method with our dummy vert method, and then we're also going to add the domain method here. So now, if you go back into Unity, you can see we've got another error here, and that's because in the domain method we also need this domain tag as well. So now you can see, let's do Unity error. Our plane, nothing really happened, but that's because our tessellation factors up here are 1. So if you change these all to 2, that's because we need to actually assign this material. So I'm just going to call this tessellation. And now you can see our plane is tessellated. If you go back into the shader again, change these back to 1, you can see it's normal again. So now the thing you probably want to do, you don't want to hard code these values, obviously. So what we can do is go up into the properties here, and we can add a tessellation variable. It's called tessellation. The standard for shaders variables is to have the underscore and then capitalized. So we can call this tessellation, and this is going to be a float and default to 1. So now we also need to redefine it in here, because this C buffer is sort of Unity's way of saying these variables are specific to each material. Up here, it's just specific to the shader. So now we can use this tessellation variable in here. And now if we go back into Unity, you can see we've got this slider here. So now if you change it, you can see we've got the tessellation. But as you probably noticed, it's only changing on the integer values. And that's because in here, we sent our partitioning to integer. So what you want to do is use one of the fractional ones. So I'm going to use fractional odd. You can use fractional even, but your tessellation is going to be a minimum of 2, which is not really something you want. So as you can see, now we've got our tessellation here. And just to note, the maximum the GPU can go to is 64, but as you can see, I don't really think you're going to be needing to go that far. So now what we want to do is, usually you don't need all the data, or the whole plane rather, to be tessellated this much, because what the player usually wants to see is up close and you're kind of just wasting all that data far away. So what we're going to do is change these tessellation factors based on how close the camera is to the plane. So we're going to need to make a new method here. So we're going to return tessellation factors, and this is going to be called distance-based tess for tessellation. And it's going to take in attributes for vertex 0, attributes for vertex 1, and attributes for vertex 2, as well as, oh no, that's it. And what we're going to do in here is we're going to create the vertex tessellation factors. And we're just going to return these at the end. So we're going to return, we're going to take this data here, and we're going to return it up here. So we're going to call calculate triangle edge tessellation factors. And and this is going to be called from here with the vertex tessellation factors that we're going to fill later. But now in here, we're not just going to use these tessellation variables. We're going to take the average of a few of these points. So we're going to do the y and z, which is vertex 1 and 2. X and z, which is vertex 0 and 2, and then x and y, which is vertex 0 and 1. And then for the inside, we're going to just add these all together and take the average. And then at the end, we're going to return the factors. So now in here, we need to actually create these tessellation factors. So what we're going to do is create a new method again to calculate the tessellation factor based on the distance of the camera. Create a method to calculate the tessellation factor based on the distance from the camera, and it's going to take in the world position of the vertex that we're working on. So as you can see, it's not compiling now, but that's because our method here isn't returning anything. So we'll work on that later. But I'm going to create a constant float, the minimum distance from the camera. So I'm just going to set this to 2. Basically, if the camera is 2 or less units from the vertex, it's going to be a maximum tessellation. And we need to create a variable up here for the furthest distance it can be from the camera. So max tessellation distance, and I'm just going to call this tessellation distance. And this is also going to be float, and we'll set it to like 20. And again, add it down here. And now we're going to calculate the distance from the world position to the world space camera position. So this is a shader method you can just use and calculate the distance between the 2 vectors. And this is a unity variable that we have access to due to this include method up here. And it just gives you the world space camera position like it says. And now we're going to create the scaled factor. So basically, if the camera is 2 or less units from the vertex, it's going to be at 1, and if it's at the maximum tessellation distance, it's going to be at 0. So basically, if you've worked with mathf.inverse lerp in C#, that's basically what this is, or vector3.inverse lerp, anything really. So max tessellation distance, what's the min distance, and this is going to be 0.0121. We don't want it to be 0 because if the tessellation factor in Unity is 0, the whole plane disappears. So it can't be 0, it just needs to be a little above 0. And we're going to clamp this, the factor times the tessellation. So basically this is just a multiplier now, and 0.01 and tessellation. So this should be 0 actually, because later we're going to be multiplying with something else. So basically, not that it really should ever be above 1, but we're just making sure the max can be tessellation and the minimum is 0. So now back in here, we need to calculate the world space position for all these vertices. So I'm just going to do that for this one, world space position 0. And this is another function Unity gives us. So right now the vertex position is in object space, which is sort of like local space or local position for a transform in C#. And this method is just turning that into world space. So it's sort of like transform.transform point if you use that. And we're going to do this and basically just copy it for everything else. And now we're going to actually finally initialize these factors. So we're going to calculate the distance for position 0, and then for the y and z, we're going to use 1 and 2. So now we can go back into the patch constant function and finally return this method. And we just need to pass in all the vertices, because remember, again, we need all these attributes here. So now if you go back into Unity, clear the errors, you can see if we move away, the plane gets less tessellated. And if you reduce the value here, you can sort of see that. And you can also increase the distance. So that's our first basic shader. The second one I'm going to do, I'm just going to duplicate this plane, and instead of, we're just going to duplicate this shader, and I'm going to call it Deformation, Tessellation. And in this shader, what we're going to do is we're going to use this height map here to displace the vertices down or up, depending on how close they are, and then also use the tessellation for that, because as you can see, if we just use the current vertices, there wouldn't really be enough to displace anything. It would just be like 2 points. So go into the new shader, and up here at the top, we need to change the name. And what we're going to do now is we need to add a variable for how much we want the vertices to move down. So it's called height deformation, and that's also float, and we'll just set it to 0 so it doesn't move at all by default. And again, add that down here. And now in the vertex method here, before we transform this position, we're going to set it here and just there. So we're not directly passing in this position. And the reason we want to do that is because we want to modify by the normal times the height deformation. And now you see here, obviously we don't have the normal, but what we can do is just go up into our attributes and we can just add it. So go to normal, and this is going to take in the normal. So now down here, it's an object space, it's just normal. And don't forget, down here, we also have to interpolate the normal as well. So now, create a new material from this, and I'll call this deformation. And now if you assign this, you can see nothing's really happening if you increase the tessellation. Now if you do the height deformation, you can see the whole plane is moving. So I mean, it's doing what we want, but not exactly. So what we want it to do is only move if it's on this height map. So what I'm going to do is assign this to the base map here. And just for visualization, I'm going to go down here and invert the color so everything's not black. And now what we want to do is sample this texture and only displace if we're like near the texture. So in the vertex shader, we're going to get the float for, so that's 4 floats pretty much for the color. And we're going to do sample texture 2D LOD. The reason we need to do the LOD instead of just the normal sample is you can't sample the texture just by itself in the vertex function. You can only do that in the fragment function. So now we're going to pass in the base map and the sample underscore base map, the UV of the vertex, and the LOD, which is 0. Color. So now we're going to multiply this by just the red channel because that's what my texture has. And that's an old error. So as you can see, now it only moves when it's at the texture. But it looks like we need to have some more tessellation for it to actually do much. And now you can see it looks pretty good. But we've got a lot of wasted tessellation here. So as you can see, on this flat parts, nothing's really changing. We don't need to have all those extra vertices that the GPU has to calculate data for. So there's a few ways you could probably do this, but the way I'm going to do it is we're going to sample at a few points. So say we only have one. So this is like the base tessellation. We have no tessellation. We're going to look at these vertices and check at a few points around their UVs. And then if any of those points are on or near the texture, then we're going to tessellate that point. And basically, that will cause the tessellation to spread closer to the texture. And over here, where there's no texture, it's just going to stay flat. So I'll put this back up for now, so you can see what it looks like. And we're going to go add a few more variables up here. So what we need is rotation iterations. So that's going to be how many times we're checking around the vertex. And that's going to be an integer, and we'll just set it to 2 for now. We need a minimum tessellation for the parts of the plane that are not close. So call that min tessellation. And I forgot these should be capitalized. Doesn't really matter, but just for preference. And I'll set this rather low, 0.01. And we also need check distance. So this is going to be how far away from the UV we're looking. Float, and I'll set it to 0.1. So that value needs to be relatively small because the way the UVs work is it's going to go from 0 to 1 at each side of the object. Here I can show you what it looks like. So right here, I'm just using the UVs as the red and green channels. And now you can see over here, as we go along to the right, this is 0 red and 1 red here. So 0x, 1x, 0y, 1y, and then 1x, 1y. So the variables only go from 0 to 1, which is why that value needs to be less than 1. Technically, it can be more than 1, and it will wrap around if your texture mode is set to repeat, but just for simplicity, it should be less than 1. Okay, so we need a few more things here. Just one more. We need proximity tessellation. And this is just how much it's going to tessellate when it's close to the texture. That's a float, and I'll just set that to 5. And now we need to go down here and add all these to the C buffer as well. Tessellation. The check distance. And approximate tessellation. So now, what we're going to do is, similar to this calculate distance test function, we're also going to create a calculate texture change test vector. And all this really needs is the UV of the vertex we're working on. And I need to define another constant here. This is pi. As far as I know, there's no constant for it in the shader itself, so we have to just write it here. And the reason we need this is because we're going to be using sine and cosine functions to offset our UVs, and those take in radians. If you haven't heard of radians before, basically they're like degrees, but instead of 360 degrees, it's 2 times pi is 1 full rotation. You don't really need to know the details for this specific limitation, but they can be useful for other functions as well. So what we're going to do first is we're going to take the sample. So we're going to sample the texture at the original UV coordinates. So just pass in the UV, no changes this time. And we're also going to keep track of the maximum factor that we can detect. So starting off, it's going to be the min Tess. So that's the lowest it will ever be. If we detect a higher change between the center and one of the other points we check, then that will be set to this. And we also want the degree increment that we'll be going for, which, like I said, 2 times pi is a full rotation. And then we're going to divide that by rotation iterations. And we're going to do a for loop here for the rotation iterations. And then we calculate how many radians we need to go, which is the degree increment times I. So that's just saying if we're not moving, or rather if we're on rotation 0, it's just going to be straight out to the right. And then as it goes along, we're going to rotate counterclockwise. So we're going to calculate the offset here. The reason I'm using half 2, this is just like a float 2, except it is lower precision, so less memory. It's not really necessary, just for slight optimization there. And then we're going to do cosine of the radians and sine of the radians times the check distance. So that's saying this is going to give us our point, like the direction we want to go, and the check distance is how far we want to go in that direction. So now we're going to take the texture sample again. I'm just going to copy this, except this time we're adding the offset to the UVs. And now what we want to do is calculate the delta between the 2 samples. So that's just the length of the sample center minus the sample. The order you do these in doesn't really matter because it's checking the length. So you could put them the other way if you want. And now we actually need to, so what we want to do is, if the delta is 0, it's going to return a 0 tessellation factor, because basically that's saying the point we got the color for has the same exact color as the center of the sample, or the vertex we started at. And then if the length is the maximum, which is going to be the square root of 3, because the maximum it could be if 1 is 0, 0, 0, and, or rather 0, 0, 0, 0, and 1 is 1, 1, 1, 1, then the length would be square root of 4, sorry, so that's just 2. So what we want to do is just take this length, and the factor is going to be the delta divided by 2 or multiplied by 0.5, because computers don't really like to do division. If possible, multiplying is usually faster. And then we're going to multiply by the proximity tessellation factor that we created earlier. And then we're going to set this max factor. So if the max factor, we're going to take the max of the current max factor and the tessellation factor. So if this one is higher, it's going to choose that. This one's higher, it's going to choose that. Pretty basic. And then at the end, we're just going to return the max factor. So that was a lot of factors. But now what we're going to do is go back into the distance-based tessellation, and we're just going to multiply this tessellation factor by the, oops, I don't want to rebuild that, the texture factor, and passing in the UVs for each vertex. So now, if you go back into Unity, turn on that, and you can see it only tessellates when it's close to the texture now. And of course, you can change how much you want it to tessellate. Right now, it's based on this tessellation factor here, which scales on distance. This proximity tessellation also sort of scales on distance, but this will just be a multiplier. And this minimum tessellation, if you increase that, you can see everything else scales up as well. And you can see here, there's some artifacts. So that's likely because our rotation iterations are only 2. Yep, you can see if we change them to 3, now it's not just checking 2 directions, it's checking 3, and you get a higher resolution. You can also have these sort of artifacts here. That's because this vertex and this vertex didn't tessellate along this line, and it can only tessellate in the middle if one of these tessellated in the first place. So usually the reason for this is you need to increase either the rotation iterations or change the check distance a little bit. If possible, you want to keep the rotation iterations as low as possible, because it's a little counterintuitive, but shaders don't actually, or rather the GPU doesn't really like sampling the texture a lot. It checks at the UV when we send it, and that's kind of expensive, so it doesn't like doing that all the time. So if possible, we want to reduce that amount that we have it checking textures. Okay, so now what you probably came here for, we're going to convert this shader into a shader graph shader. So we're going to create, go to shader graph, and it's going to do a lit shader graph, and I'm just going to call this tessellation. And basically what we're going to do is we're going to kind of inject our tessellation logic into the shader. So how we're going to do that is we're going to use a custom function. And the reason I said at the beginning you need Unity 6 is because of this use pragmas they added here. So as you might have noticed at the top of our normal shader, we've been using these pragma whole, pragma domain, and we're going to use those again in this custom function to sort of hijack it into making the shader graph tessellate. So we're going to need to create a new file. So it doesn't really matter what it is. So I'm just going to call this, or we're going to create another shader again. I'm going to call this one force tessellation. And I'm going to open this in File Explorer. Okay, so here I am in my assets, and we're going to go here, force tessellation shader. I'm going to change this from .shader to .hlsl. It'll warn you, be like, it's unstable. It does not matter. Your ID, you'll probably close it. And now if you go back into Unity, you can see it's this different file. And basically we want to delete everything in here. So now we can drag this HLSL file into the source here. The reason we need to change the extension was you can't drag in the normal shaders. So we're going to drag that in, and the function name is going to be called force test. So now we need to create that in here. So it's going to be called force test, and you need to do underscore float. The reason being, I mean, return float rather. In the shader graph, we're going to have our output as a float. It's going to be called dummy. And shader graph automatically generates the underscore float because the output has float there as well. So if you don't add the underscore float, it's going to complain saying it can't find your stuff. So what we need to take in our inputs is the UV, so that's a vector 2, the world pause, which is a vector 3, and the world normal, which is also vector 3. So the reason we need these is because if we do not include them, shader graph is optimized in a way that it will just not send the data to the shader. So if we don't pass it in, our custom function will be like, where's the world pause you're asking for, but we don't actually have it. So we need to pass in UV, position in world, and also normal vector in the world. And then we're going to add just going to add a color for now. So this could be color. And what we're going to do is just going to add this to the color here, and then set that as the color of the shader. The reason we need to add this is because if we don't, shader graph, like I said, it's pretty optimized. So if we don't have this connected to anything, it will see it's not connected to anything. So it's just not going to do any work for it. It's not going to compile it into the shader. So we need to force it to by adding it there. It's not actually going to do anything adding it, since this dummy thing we're just going to set to 0 in the shader. But otherwise it will compile. So now, as you can see, we're getting some errors. It's saying it can't find our function, but that's because in our force test function, we haven't actually set up the inputs. So we're going to do the UV, the world pause, and the world normal. The names don't have to match unities, but you have to have the same types. So like vector 2 becomes float 2, vector 3 becomes float 3. And then we're going to set out, which is the dummy float. And we're just going to set this to 0. And this should actually be void. I messed up. So now, sometimes shader graph gets a little annoyed and will error out even if you don't have any errors. So if you just close the window and then reopen it, as you can see, the error is fixed, even though it was saying it wasn't. So now I'm just going to create a material, and I'll call it the shader graph tessellation. And this isn't actually going to do anything right now. It's just going to be a basic shader. I'll set this to white. And now we need to actually add the tessellation logic. So how we're going to do that is we're going to create another HLSL file. I'm going to call this tessellation logic. And now in here, we're basically going to go into our deformation shader, and under this HLSL program, we're just going to copy everything here until it says end HLSL, and we're just going to paste it in here. So you can see the indentation is a little messed up. You can just fix that. And we don't actually need these vertex or fragment functions anymore because shader graph is going to do those for us. So we also, so I can delete the fragment function, but we still want to have the vertex deformation. So instead of having it return varyings, we're just going to make it a void. Can you move all this out stuff? We'll be fixing that later. And just call it here instead of returning it. So now, this is where it becomes a little tricky. So first off, we need to delete this include because shader graph does that for you. Unfortunately, that will cause a few errors because your IDE doesn't know that it's being called in shader graph. That's kind of the whole point of the injection. So it doesn't know that these variables will exist when it's being run. We also need to do is add all these variables in shader graph. So we're going to go in here. We need texture called base color, a float called tessellation, max tessellation distance, height deformation, rotation iterations, min test, check distance, and proximity tessellation. You can change the names of these here, so I'm going to go through, so change this to deformation map. But as you can see, it changes this reference here, and we need this to stay the same. If we don't make this stay the same as in our code, it will error out because it will not be able to find this texture. So I'm just going to call this. I'm going to go through the name all these. Okay, and for the rotation iterations, you can remember we created that as an int in our shader here, and you can do that in shader graph as well by going to this mode and just setting it to integer. So now nothing will have really changed except we added all these variables. Now to actually get our logic working, we need to go into this force tessellation, and at the top we're going to go hashtag include, and we're going to include tessellation logic.hlsl, and this needs to be in quotation marks. So as you can see, this is now including, it's going to include all this code in this force tessellation function. But right now it's grayed out because it's not actually, we're not doing anything with that code. But what we want to do is we're going to copy these whole and domain pragmas, and we're going to put them in here. So now the shader, it's telling shader graph, use the whole method from this tessellation logic file, do the same for the domain, and that's the reason we need the pragmas, the use pragmas in this custom function. And now we're going to get a bunch of errors because we're using redefinition attributes. So we can't use these attribute invariants. We need to use the ones shader graph gives us. And we also need to delete all these variables because shader graph has those as well. So now instead of attributes, what we're going to be using is called packed variants. It works basically the same, but the reason we use these is shader graph will sort of compress all the data into these packed variants for like memory, I believe, and it uses those for most things instead of attributes. The way you can see like what data is in these is if you click on your shader graph and then click view generated shader, you can see it generates this whole multi-thousand line of your shader graph code. But what you only want to search for is do Control F, and you can search for packed variants. Here it is, and these are all the positions it gives you. So position world space, normal world space, text chord 0. This is actually our UV, even though it doesn't name it that. The reason it has that is all the vertices, all the vertices have texture coordinates, is what they're called, which can basically hold almost any data you want, and the UV is usually stored in text chord 0. So now back into the tessellation logic, we need to just replace everything using the attributes with packed variants. And we can also remove this dummy vertex method. We're not using that anymore. In the vertex here, we actually need to change this from just being the packed variants to being in-out packed variants. The reason we have that is otherwise it will just pass in sort of a copy of this data, and when we change the position here, it won't actually update the original one we sent in. If we do in-out, it will send the actual copy, the original version, not a copy, and that way it has the correct data. Down here in our domain, we also need to change this and change the attributes here from data. And now one sort of special thing here, we don't really care about interpolating all of this data. So what we're going to do is 0 initialize and packed data. So basically what this does is um, it sets pretty much all the data points in this packed varyings equal to like 0. So right now they don't actually have a value until we run this 0 initialize. And the reason we need to pass in the packed varyings is it's sort of like get component in C#. You need to add the brackets and then like the component you actually want to get. It doesn't know otherwise how you want to do it. And then down here, these, and we need to turn the data at the end as well. We don't actually have these things anymore. As you can see, we need to go to the packed varyings, and these are the ones we want to interpolate. So we want to interpolate position world space, normal world space, text chord 0. Make sure you capitalize this C. It needs to be capitalized. And then the clip space as well. And also the tangent. So now if you go back into Unity, you can see you still got some errors. And that is because we're not using the object space anymore. It just gives you straight up world space. So we can remove these and just use position world space right there. And we're also not using the UV, we're using text chord 0. So replace all the UVs, the text chord zeros. Same up here as well. And this also needs to be position world space. And we can just modify that directly. Also need to change this to normal world space. And now you can see it's loading a little longer, and you've got our shader compiling. But as you can see, it's kind of just gone. And the reason for that is we need to re-update the clip space positions after we change the normals. Otherwise, it doesn't really. We change the normals, but in the fragment shader of shader graph, it doesn't know where the clip space spot is. So we're going to do object pause transform world to object. So this is the same as the one we used earlier, except the other way around. It's going from world to object. And now we set in dot position clip space is equal transform object to h clip. Pass in the object pause. So now got an issue here. I've misspelled this. So now it's compiling again. And it's still gone. Let's see. Right. Okay, so the reason it's gone is because, like I was saying earlier, we need to increase our minimum tessellation. If it's 0, the object will disappear. So it needs to be above 1. And I'm just going to go and copy all these variables from here. 10, 20 distance, 5, 5, and then 5 for proximity tessellation. So now you can see we've got it all lit. And as you can see, though, it's looking a little weird in these spots down here. And the reason for that is, although we're offsetting the positions, we are not actually changing the normal vectors on the sides of these slopes. It is possible to do that, but this tutorial won't be going over them. It's easier to just add a normal map, and it will usually offset the weird looks here. But that about completes it for this tutorial. You can see we've got the distance working as well. And now you can pretty much do anything you would in a normal shader graph shader. You can change the color, normals, whatever. but also using the tessellation, which you would not be able to do without HDRP normally. So I hope you enjoyed the tutorial. Leave a comment if you have any questions, and thank you for watching. One thing I forgot to mention, I will leave a link to the GitHub project for this Unity project in the description, so if you want to visit the code yourself, you can see that there. Thank you. Bye.